Have a good day. We are Group 1, and today we will be presenting our group project second delivery for artificial intelligence and adaptive systems. The project explores how nature-inspired algorithms can be used to optimize trading strategies, especially in context of the Bitcoin market. Now I am moving to introduction section. I would like to say that artificial intelligence has enabled development of adaptive trading systems that can respond to the volatile and unpredictable nature of the financial market. In this project, we apply meta-heuristic algorithms inspired by natural processes to optimize the pyramid of trading strategies, particularly those used for the generating buy and sell signals. The key goal is to minimize profit by identify the most effective parameter configurations, and we train our models using daily Bitcoin data from 2017 to 2019 and then tested their generalization ability on data from 2020 to 2022. The algorithms were evaluated based on three main criteria. First one is profitability, particularly on unseen tested data. Second one is convergence behavior during training. And finally, computational cost by considering runtime and efficiency. Now we're going to talk about the algorithms we investigated. The first one is ant colony optimization. Actually, this one is inspired by how ants find the shortest path to their foods using their pheromone trails. In our context, it constructs solutions step by step through the stochastic process, with ant reinforcing the most successful paths. So the version we explored, actually ant minor one, improves upon earlier models by using direct acycling graphs to represent the search space, and also interval rules leads to better handle continuous features. That's all about the ant colony. Then we are moving to hybrid genetic simulated annealing one. This algorithm combines with two components. First one is genetic algorithm that allows to population of solutions, and simulated annealing which allows occasional waste moves to escape local optima. So this introduced adaptive cooling schedules and multiple mutation strategies to increase diversity over there. So and begin with the heuristic based population generation and alternates between genetic operation and local refinement across generations. Now we are moving to most crucial algorithm, improved graph optimization. So improved gray wolf optimize is based on hierarchical hunting behavior of gray wolf, actually using the alpha, beta, delta rows to guide the search. It improves the original gray wolf optimization by introducing nonlinear decay to control exploration more smoothly and Gaussian mutation to maintain diversity and escape local optima. So now we are moving to fourth one, the PPSO. The phasor practical sum optimization built on the standard PSO, but replaced with the fixed hyperparameter with dynamic phasor-based functions, which are derived from the trigeometric phase angles. This allows each practical particle movements to be self-adaptive, creating mix of the cognitive and social behaviors to vary with each every iteration processes. The final algorithm we examine is modified firefly algorithm. Actually, this one is based on behavior of fireflies, where individuals are attracted to each other with brighter flashes, which represent the better solutions. This one is enhanced the basic firefly algorithm by adding few steps to there. They are the crossover and mutation operation, quasi-reflection learning, and the dynamic step size. So this is all about the algorithms we investigated during the other process.
We will now talk about how we designed our trading bot and the different parameterization strategies that we explored to be able to guide the optimizer. So when designing our bot, our first design goal was the fitness function. We initially considered multi-objective fitness functions, such as ones penalizing volatility or drawdowns, but introducing those metrics significantly increased both the number of parameters and the computational complexity, making optimization harder and less interpretable. So for our bot, we simplified the fitness function to focus purely on final profit, measured by the cash balance of the backtesting. This gave us a clean, single objective optimization target and reduced the evaluation time. The core of our bot is built from a combination of weighted moving average filters. We took the ones mentioned in the project specification. So the simple, linear, and exponential moving average filters. Each filter is defined over a window of price history, and we normalize each filter to preserve the scale. These filters are then combined using weighted sums to generate high and low signals. We detect sign changes in those signal differences to generate buy and sell decisions. So for example, if a low signal crosses above a high signal, then we trigger a buy, and if a high signal crosses over a low signal, then we trigger a sell. So now we talk about the different parameterization strategies that we explored when building our bot. The first one is the simplest one. It is the two-dimensional simple moving average strategy. It computes two SMAs with a short and long window size, and buys when the short one exceeds the long one, and sells when the long one exceeds the short one. Next is the three-dimensional MACD. It uses exponential moving averages with a short, long, and a single span. It uses the difference between two EMAs to calculate the MACD. This is then smoothed by a signal EMA. We then calculate the histogram by the difference between the MACD and the signal. And the buy and sell decisions are triggered when the histogram crosses 0. Then we have a more expressive 14-dimensional model. This is the same model which was explained in the project specification. It separates signals into high and low channels. Each channel is a weighted combination of SMA, LMA, and EMA, giving us 7 parameters for each channel, giving us in total 14 parameters to optimize over. We buy when a low channel signal crosses a high channel signal, and sell when the opposite happens. Finally, we have our custom 21-dimensional MACD strategy. It has 3 independent filters: the fast, the slow, and the signal lines. So this gives us this vector to optimize over, which is again a 7-dimensional vector, and over 3 lines, that's a 21-dimensional optimization problem. So we use the difference between the fast and the slow signal line to calculate the MACD. This is then smoothed by the signal line, and we calculate the histogram by the difference between the MACD and the signal. And the buy and sell decisions are again triggered when the histogram crosses 0. So we experimented with all the different parameterization strategies that we mentioned in the slide before, using a population size of 30 and a maximum iteration count of 100 for the experimental setup. We saw that the 2-dimensional and 3-dimensional models underperformed compared to the 14-dimensional model. This was because they were far too simple to be able to capture meaningful trading behavior. The 21-dimensional model also performed poorly, and this was because 21 dimension was far too large to effectively search with just 30 population size. We ran extended trials with population sizes of 100, 200, and 300, saw some marginally better results compared to just 30 populations, but it still couldn't beat the 14-dimensional model. As such, we would have to increase the maximum iteration count to have a more coverage of the solution space, or even increase the population size even more, but that will increase the cost of exploration, and we decided to not go ahead with the 21-dimensional model, but instead chose the 14-dimensional parameterization strategy, as it performed the best out of all the other dimensions, and it struck a balance between expressiveness and search cost.
Here's how we picked the right algorithm. Over the next 2 slides, I'll show you how we judge each algorithm and why we selected 4 of them and dropped 1. Let's dive in. Our screening framework mirrors a procurement scorecard. First, implementation complexity. If an algorithm can't put into our pattern stack within a day, it's out. Second, search strategy diversity. We want at least 3 distinct paradigms to hedge algorithm risk. Third, proving financial stability. Peer-reviewed wins on price data. Finally, compute footprint. 60 agents times 50 iterations must wrap in under 3 minutes on a laptop. Only 4 algorithms passed every gate. ACL refined solutions with fairer materials, great for balancing exploration and exploitation. HGSA adds genetics exploration on gravitational backbone, then cools locally with mutated aniline. IGWO ranks Wolf's depth search pressure via nonlinear decay, and Springer's cancer mutation, perfect for high-dimensional resilience. PPS injects further dynamics into classic PSO, keeping the swan diversified and nimble. Together, they form a diversified optimization of portfolio. Modified Firefly algorithm looked attractive, but its performance is hypersensitive to step size and the attractiveness decay. It result shows limited edge in continuous low-dimensional spaces, so we drop it. Keep the scope clean and the schedule tight. Thank you. Now we move to experimental design.
Hi, I'm Runtian. I'm going to do the experiment and evaluation part in our project. For the dataset we need to use to generate information, we picked the daily Bitcoin history. We did try to use minutes history to test our boat, but even started on an easy demo that taking a very long time. Undoubtedly, you will consume more time on experiments and modification. So the daily one is fair enough and give a deep view in this dataset. It includes some kinds of Bitcoin price every day from 2014 to 2022. Then we choose some range of them in training set and to analyze on how it will affect the final profit to different optimizer. This line chart shows the longer range of training data generally give a higher profit, and most of them start to go down fast from 2016 to 2017. This reminds me that Bitcoin may not be very popular before that day, so people can get higher profits if buy it earlier because we set test sets from 2021 to 2022. Because the small dataset we use and evaluation on space consumptions makes us realize that memory analysis in our case is meaningless somehow. So we just plot the time consumption here. You can see that besides of MACD mode, the cost on time must go higher as increasing in dimensions, from 2 dimensions to 14 dimensions and 21 dimensions. The MACD one even higher than 14 dimensions one is because it requires multiple calculations of the EMA, where each step depends on the previous one. Here we text the final profits of each optimizer based on whether apply early stopping or not. Generally, in this figure, set patient to 5 means if those optimizers can't find better solutions in 5 steps, then you will stop. And it gives us a slight improvement in that case. For 14 dimensions, we consider only, and whether we tweak, the trend keeps same. The parameter bounds may impact the final profits as well, so we explore the effects of bounds in 2-dimensional SMA. We can see here is the shorter one between 5 to 200 make better profits than longer one, but in the text sets in contrast. To figure out what happened, we look at the dataset we are. Thus, the reason is the training set is smoother than the test set. Smaller window size can catch tiny change better, and larger window size can make more patient. As the combinations in exploration and exploitation, we recognized overfitting behavior was going to happen. As the text and training sets have some different properties we outline in our report, and so we limited the bounds to 200 to reduce the computational costs.
Let's now look at the key results from our experiments comparing the performance of these algorithms. First up, we will look at the impact of different hyperparameters on performance. We'll use these for the later tests. We'll then look at the speed and quality of convergence on training data before looking at performance on unseen test data. So, how do hyperparameters impact performance? Here we have 2 variables, population size and maximum iteration, that we have experimented with. On population size, we've set maximum iteration to 30. We can see by around population size 60 that all of our algorithms outperform CCS, the one in purple, that is our single-state deterministic algorithm. Similarly, in maximum iterations, we see that by around mark 50, we get the same outperformance happening. We've also assessed early stopping, for instance, ending at 5 stagnant iterations with some tolerance value. That gave us minimal improvements, so we have not included it here. Finally, we learned that we should use population size 60 and maximum iteration of 50. The next question we asked was, how do these different algorithms compare in training? In this chart, we see 9 randomly seeded convergence curves, and a convergence curve basically shows you at each point in the iteration what is the best value that has been found by that algorithm. We can see here, for instance, that the Grey Wolf Optimizer and PPSO, the ones in red and green, seem to be outperforming the other ones. We can also see the other ones maybe plateauing a little bit when we get to a specific value. But this is only 9 samples run on training. To be able to make a proper good inference, we should run it on more cases, and that will give us an understanding of the tendencies of each algorithm. So here we see exactly that. We see the performance of those algorithms on testing data. So for the testing data, we've used the data from 2020 to 2022 using the 14-dimensional strategy. We used 100 samples on population size of 60 and maximum iteration of 50. The results here are plotted as a box plot, and t-values and p-values of pairwise t-tests have been shown. I've highlighted the ones that are statistically significant at 1%, I think even 0.1%. Based on these results, we can see that all of our algorithms, for one, did better than CCS. Secondly, we can see that Grey Wolf Optimizer seems to outperform all of the other ones at a statistically significant value. So these are our findings. So that's it. Over the course of this presentation, we've looked at different solution spaces. We looked at 21-dimensional and saw that that's too expressive, while the 2-dimensional seemed to be not expressive enough. We decided on some algorithms to assess and some restrictions on the dataset based on what we could understand of the function and its computability. We also tested the optimizer's parameters as well as the performance on unseen test data, and found that Grey Wolf Optimizer seems to do the best for our specific case. Obviously, there could be more things that can be done. Some of the things that we could suggest include different languages, for instance, looking at generalized weight moving average. Another thing we could do is alternative indicators, something that can show maybe volatility or risk that is apparent in that area. In the same vein, we could look at different evaluation metrics. For instance, Sharpe ratio is something that comes up a lot. Different dataset sizes and granularity should be explored. We are not yet sure if the Grey Wolf Optimizer is good for all types of granularity, all types of datasets. Finally, we should also have a look at looking at the space, the function space, through dimensionality reduction to see if there are any landmark features that we could exploit. That leads us to the very end of the presentation. Thank you so much for this optimization investigation. It was a very interesting case to study. and thank you for listening.